So I'm going to present a little bit StumbleUpon, the problem space, what we're trying to do, how we historically, I can say historically, since this company is 14-year-old, we solved the problem. What are the limitations of the current architecture, and what we are planning moving forward, and how this is relevant for Scala, you know, passionate people. So, according to a study done from our marketing group, there are over 30 trillion unique web pages in this moment of the web. And in average, people just visit 3 or 5 different sites each day. So, StumbleUpon trying to solve this problem, try to take content and convey this content to people that is actually not searching for that particular content. Let's say that you have a really broad interest and you want to find something that can fit your interest, but you are not having any keyword in mind. So StumbleUpon trying to work in this space and trying to basically give you this personalized experience around some interest that you declare. In general, how do consumers find new content? Well, there is a search engine. You have a particular information need. You type some query, and you retrieve a list of relevant results. There is discovery. That is what we are trying to do. You're not looking for anything in particular, but still you have some time to spend in a, let's say, useful way. And so you try to obtain some content from the web. And there is the social feed. It can be Facebook, it can be Twitter, or any other social network you usually use. StumbleUpon is not a search engine. StumbleUpon is not a social network. Even if people often basically think that we work like a search engine or we work like a social network. Why it is different? What are the challenges that we are trying to solve at StumbleUpon and that are not actually a problem for search? Discovery is serendipitous. Again, you do not have anything clear in your mind. Let's say that both Alexi and I follow Scala, okay? Probably the content that is good for me is, I don't know, naive for Alexi and vice versa, right? So even if we are looking for, or we are searching for same content, what is good for us, it's totally different. Nevertheless, we expect that the discovery engine will be so smart to understand that there are different levels of interest in a particular topic and convey the right content to the right people. I would say that search does not have this problem. Search is intent-driven. You know exactly, or with a good approximation, what you are looking for. If I say I'm looking for the address of a particular restaurant, you can find it, you cannot find it. But you know how to evaluate the result, and the search engine knows how to evaluate the result. Discovery is more challenging because it's once at a time. So what's happened with discovery, you just are exposed with a particular piece of content. There are 2 reactions. You like it or you don't like it. Search engines have more than one chance to satisfy you because you are presented with 10, let's say in general, 10 results. I come from research at Yahoo for many, many years. Yes, there is a lot of investigation if your result is in first or second or third position. But the reality is that from a user perspective, if that address is the 3rd result that you find, you are still satisfied. Discovery never repeats. This is what it means. Once you're presented with a particular piece of content, this piece of content will not show up in any future session. This doesn't happen with search. And in fact, the search basically is used as bookmarking tool for many, many users. This is one of the top usage of search engine. If you don't want to memorize a particular URL, you memorize the query that allowed you to find that particular URL. So it's a bookmarking tool. Discovery, adapt. What does it mean? Since we try to personalize the feed, even if we are, I don't know, if you are looking for a particular topic, and since we submit content continuously, day after day, you will not have the same experience in 2 different days, even if users are similar. This doesn't happen again for search engine. Results in the most of the cases are fixed. There is a change that is less than 10% in the vast majority of the result set of the query. And last, but I would say most important, discovering is tailored. It's trying to personalize and try to understand what you like or what you don't like. Search is still totally impersonal. So how we do? So we collect a number of signals that are implicit, like the interest that you like, could be dogs, photography, music, but also we try to understand other implicit signals. So for example, let's say that we observe that usually you prefer trending content with respect to evergreen content, something that we learn while we are using, or we can actually use, we have a mechanism of friendship that is similar to Twitter. And so we can present you with content that your friends like. We use also collaborative filtering like algorithm. So if there is user similar to you, we actually present you with the content that they like. And we also use experts. Experts are people that seems to better spot good content. So they like content that the vast majority of the people that follow a particular category likes. And we use this ensemble of signal to basically recommend content. How do we do this? This is our zoo. A lot of animal, whatever it takes to get the job done, right? And okay, I know you are Scala enthusiastic, but I have to admit, it's this. Well, but 14 years ago, so, but in 14 years, what's happened is that the big elephant in the room is actually not Hadoop, but it's PHP at this point. But we're moving, so the amount of code that is written in PHP is decreasing, the amount of code in Scala is increasing, and we are much happier now than not a couple of years ago. Nevertheless, this is the architecture overview. So let's say the architecture that I inherited 6 months ago when I joined the personalization group. So there are many different pieces that allow us to do the job. So in a nutshell, new content needs to be ingested. This happens with RSS feed, so automatic way, or through discovery by user. Enter in a content analysis pipeline in which we do a number of filtering, boilerplate, and some analysis, keyword extraction, pass to a sampling pipeline which we kind of try to understand how good this content will be, how it's going to perform once we will put definitely in front of the user. After this pipeline, the most of the content is thrown away, do not pass our threshold of quality, and around 5% of our content is actually indexed and is shown to the user. How we do this? We have a lot, and I will say a lot again, of offline machine learning models and heuristic and whatever you have in mind. Yes, we use them all. That basically every night or for trending content news every hour, do some magic, some computation. This content is then served real time through our recommendation engine, most of the case using Elasticsearch. There is some part of our pipeline that actually use online events for some computation and through Kafka, and these signals are basically used to create, I would say, the final repository that is used runtime. These are the basic component, but there is much more. These are all the other subsystems that actually help us to have the job done. And there is the advertise service, the URL score service that is very important for us, that compute a sort of quality score of each page in our indexes, and so far so on. How good we are in doing what we are doing. These are our big numbers. We have 3 billion of total stumble, more or less, per year. We have 100, actually there are more now, are 190 million content in our index. These are the lists that people use to aggregate their content, to retrieve the content, 10 million. And these are the amount of page that we add to our index per day after throwing out 95% of the content that arrive on the door of StumbleUpon. Okay, so this is very, very broad introduction. It works. We are in this business since 14 years. People do not complain of the quality of the experience. What we can do better, okay? And why we need Scala for doing it better. Recommendation model. How many of you are familiar with machine learning in general? Okay. Do you have any question for me? I put there a bunch of keywords, right? Machine learning basic, machine learning basic course, you know, the one that you take on Coursera, stands for the basic course. So we use them all. For a reason or another, we use them all. There is a question that you want to ask me when you say this. Prediction.io, there is any question that you want to ask me?
What tools do you use to build algorithms? Do you use existing algorithms, or do you write it from scratch?
Well, this kind of stuff is, I would say, is very basic, right? We use what is available. We don't use anything fancy. But if you are passionate of machine learning, you will notice that here there is nothing fancy. What is matrix factorization? What is it? I didn't mention. It's not here. Why it's not here?
That's a way to decompose a matrix.
Huh? Why we don't use it? I mean, you probably heard about the Netflix competition, $1 million throwaway to improve matrix factorization based algorithm of, what was, 3%, 4%. Never used that. We didn't even try. It's not here. Why? The problem is, I mean, in the machine learning space, there are false problem and real problem. Having performant algorithm is not a real problem. There are many other real problems for which we need better. So multifactorization is biased. It's biased against items that tends to concentrate the most of the ratings, right? What does it mean this? It means that in any business around recommendations, think about Netflix. There are a bunch of movies that collect the vast majority of items. Well, since they collect the vast majority of items, why do you have to use multifactorization? Just go with them. It worked pretty well. And multifactorization will be biased against that item. There is another problem in real space, real recommendation, not the one that you read about in a research paper. What is the real problem? Is the power law curse. You know what is the power law curse? The power law curse is that in real space, when you have a user, people that does stuff, data distributed as a power law. So there are few users that likes everything. There are users that not like everything. In the search space, it's the same. There are query. You know what is the top query in search? At least when I was working at Yahoo, was Facebook. Can you explain me why the top query in a search engine is Facebook? I never understood user, and I continue not to understand user, but nevertheless, million and million of queries every day from unique user about Facebook. Okay. We are here, and we have exactly the same problem, guys. So the problem is that so when you do machine learning, you need to train a model. What do? You sample at random, big mistake, from user. So this is exactly the same power law. So this is the head, this is the tail that I enhanced. So think about this being somewhere here, right? The problem is that in general, when you start sampling a random on user, just random, at some point you realize that you sample 78% of the user, but still you have in your user item matrix 5% of the ratings. This matrix is extremely sparse. What do you want to do with this matrix? Nothing. And you know why this happened? This happened because there are 5% of your user, just 5% of users of StumbleUpon, that actually are responsible of 72% of the ratings. So you can do two things. Or random sampling user, and so you will never get enough rating, extremely sparse. Or you can sample ratings. So you're sampling are sampled from the end of your power law. And so what you have that you're sampling from user, they like everything. Why do you want to even think about create a prediction model for them? They like everything. They have the tendency of like everything. So I'm just spending my time to do nothing. When you start doing the job like you are taught at the college, sample at random, take some likes, put in your matrix factorization black box. Oh, usually interns come to me and say, Debora, I have 97% accuracy. Yes, but you are not predicting anything because this model is not going to work on real user. When you're bucketing in a smart way and you use the state-of-the-art matrix factorization, LAS, whatever it is, your real accuracy on your product is this. Do you think I'm going to productionize this model? No. I mean, 63%. Why should I? It's near a coin. So what? So what can help us to do a better job and actually enable machine learning in a meaningful way? Is a question of more data? No. It's not that you will convince user to rate more, right? What are you going to do? Paying them? Please rate? No, they're not going to do it. Better model? No. Why I should use an ensemble of machine learning algorithm, the famous Netflix, 1 million model, to what? To improve my performance of what? 2%? 3%? I'm not going to bother. So if I improve 3%, I pass from 63% to 66%, I'm not going to productionize either. So what? We need the smartest data. And how we get there? We needed to model. We needed to use machine learning to better understanding user before feeding some signal to eventual multi-factorization algorithm. And when I say smartest, what does it mean? You need to understand your product. You need to understand your user. So what I'm plotting here is the time spent from 3 categories of user: the one that rates, the one that do not rate, and the one that thumb down. Okay? What is strike to me? Usually there is this concept of dual time. The more you stay on the page, the more you like. Okay. Usually people that like in the first few seconds that they see the page. So the most of the like happen before you actually read the content. Instead, for dislike a page, you actually need a little bit more time. I think that the reason is because you need a kind of emotional reaction. Oh, I'm really pissed off. And you thumb down. These are content that is not rated. This is the time spent of content that is not rated. So, obviously, these are signals. And these are not 5% of your index, 5% of your movie, 5% of whatever you are selling, if you are Amazon or whatever it is. These are all your Stumble, all my signals. We have a model. I don't want to enter, but we have a model that actually uses implicit signal instead of ratings. Using multi-factorization on this model actually brought us to an accuracy of 86% from the original 63. On this kind of smart data, I can actually try to do some improvement from the pure machine learning side. But before, I need to be here, before to trying to improve the performance of my algorithm. Training time is not a bottleneck. I went to a lot of meetups and a lot of which people say, oh, we can train your model in a cluster of 1,000 nodes in 3 minutes. Why should I care if my training takes 3 minutes or take 15 minutes? I mean, this is not really the problem. So what is moving forward? So, and where we need to modify the architecture. To have this smart data processing. And here is the real performance bottleneck for StumbleUpon and for a lot of recommendation-based company in the area. So this is something that is a project that is currently ongoing, and that is the creation of this pipeline that is based on implicit signal but not rating. Our current data infrastructure are characteristic as this. I would say average, okay? It's a few hundred of MapReduce jobs and workflow. We have cluster on around 1,000 of node. We use Scala, Java, Scalding, Pig, I, whatever it takes to get the job done. Serve us well over time. I have to say, StumbleUpon rely on this data pipeline. But what if you want to use implicit signal? So what if you want to actually inject every single stumble as a feature to compute the quality of each page? We're talking about a real-time data pipeline. We are talking about better understanding trending URL that are trending just for a couple of hours, so that are not captured by the nightly crop job. They are already, in the decline. How we do this? So this smart data pipeline rely on a number of signals that are aggregate signals. Think about variance, or think about median over a stream of data. How do we do this?
Storm.
That's the answer. That's the answer. And actually, to tell you how we do this, I will pass the microphone just for a couple of minutes to Sam. Sam is actually building this, and
so as Debora said earlier, we don't have a real full-fledged real-time data pipeline yet. Most of our data processing is done on MapReduce jobs and other offline recommendation systems. The first thing that we are trying to move to real-time processing is the real-time URL scoring. So because we are moving towards a real-time event system, we are also thinking about making the URL scoring logic much more robust. For example, like URL score is not just a one-dimensional scale of quantity. It can be scoring by multiple buckets, which could be based on your demographics or based on your device or a combination of all of these. So we are coming up with a comprehensive topology. Obviously, it is a strong topology that would increase the real-time availability of these scores, and will also expand the scope of what we mean by scores. So the main infrastructure that we use are all of the events that I talk about here are consumed from Kafka, and we use a combination of Redis, Cassandra, and HBase to store the scores, as well as use Redis for intermediate caching. So this would eliminate a big chunk of our offline recommendation and ETL pipelines. So the rough idea is something like this. We have events coming from Kafka, and this is a strong topology that uses Redis and Cassandra for some data caching, and then we have some processed data from historical data on HDFS and then on HBase, and then we merge these and then produce the final result. And that is usually stored on Elasticsearch or HBase itself. So that's roughly what we are trying to do. Yeah, that's it.
Thank you. So yeah, this basically concludes our presentation. So this is just a use case. We are actually moving to a different topology, a lot of our subcomponents in this moment. And we basically planning to, to take our PHP elephant out of the scene ASAP. So we are looking for people to help us to, realize our vision using Scala in the next future. So if you're interested, this is the address. Thank you.
Do you want to take any questions?
Well, if there are questions,
yeah. We'll do some questions, guys. Just please repeat them for the...
Yeah. Yes, sure.
So why are you moving from PHP to Scala?
When?
Why?
Good question. Why? So the question is why you are moving from PHP to Scala. Again, the vast majority of our processing, I would say, is sequential processing. We have this code base that is actually was built over 14 years, and we have a code repository in which basically we don't have in this moment component. We have what we call the big ball of mud. So reason is that when you start, approaching the problem of computing some feature in real time, and you basically finally needed to solve a problem like thousands and thousands of signals that in a distributed setting arrive on the door of your machine learning. So basically, the tool to get the job done are totally different. So we approach as company, Scala 2 years ago, and the problem of scalability. How can we make this scalable? How we can actually have a signal that becomes part of our score in real time. There was a huge learning curve, but there are, as this gentleman said, screened before, storm. Yeah, so the idea is to move towards tools that allow us to scale in a better way. And this is now PHP. Will be anachronistic, right? Start doing something with a technology that is 12-year-old.